So we know from when we see div A is equal to rho, if you tell me this entirely specifies the acceleration, I know right away that A is a gradient of phi. Otherwise, this would not specify it. Okay? So this is my field equation. Div A is equal to rho. Rho is a function, a number. A is a vector. So remember what we said before, a vector has 3 components. Div A just gives you a number. How can we reconstruct what A is just given that number? The answer is, it's the fact that A is the gradient of a potential. Now, in Newtonian gravity undergraduate, you just use that. You don't even know like why it's there. You use it maybe to derive the energy equations. You can solve problems more simply and so on. But you don't really get to see necessarily how it tells you something deep about the theory itself. Okay? So what? Big deal. Of course, 1 over r squared is obviously the derivative of 1 over r. Haha. So what? Obviously, right? I mean, what's the big deal? Right? So at that level, it doesn't really look like much. You're using some mathematical trick, fine. Instead of 1 over r squared, say it's the derivative of 1 over r. But the point is, in terms of the geometry of space plus time, or really in the full theory of space-time, it tells you a lot about space-time. Okay? The fact that you have this extra information enables you then to derive your world line curvature from it. It tells you, what it tells you is something profound about space-time that I'll just touch on now, and we'll finish this lecture with that, and we'll go on much more deeply and develop that whole level, just like we had a lecture and a half about the gravitational acceleration and a lecture and a half about the tidal acceleration. We'll have a lecture and a half about this next level. We have these 3 Riemann components added together to give us Ricci, which then equals a number. There's no way to get the 3 components separately from one number, one function. We need more structure in order to be able to specify each of these 3 tensor components, each of these tidal acceleration or Riemann curvature components from one number. We saw the connection curvature, we saw the Riemann curvature above it, right? We saw how they're related. We now know that the Riemann curvature components are easily simply related to the connection curvature, right? And we can only have the field equation that we have because of that structure for a local theory. But there's still a problem because there's not enough determinants. So clearly there's yet another level. The next step is to go to a 3rd level. And that's what we do in the next step. The next step we'll see what is the level below the connection curvature in the same way that the connection curvature is below the Riemann. You'll have the Riemann level, below the connection curvature, and below it something else. Okay, the Riemann curvatures were derivatives and products of the connection curvature, right? Derivative and products of the connection curvature. And the connection curvature will also be related to the thing that's below it. Okay, can anybody make a stab, a guess at what that might be? Mathematically and physically. Okay, think of the equations and something that we did today, and think of the way that the connection curvature was related to it mathematically.
World line curvature?
Well, the world line curvature is the connection world line curvature we're talking about.
Right.
What might it be related to? We saw a new example of connection curvature today. What was it related to? It was a purely spatial connection curvature, right? How was it found? How was it computed? Okay, in the handout, how did we find the values of the connection curvature? What did it come from? This spatial connection curvature.
It was just the differential.
Right. Of right, it was these derivatives of these metric coefficient things, these little g's, right?
Yeah, okay.
Right? In the same way, the connection curvature of the world line, the space-time connection curvature, will also be the derivative of something having to do with a metric, but it'll be a space-time metric. Okay, the spatial curvature, connection curvature things has to do with the fact that the coordinate lines curve, and the world line curvature will be derived from the fact that the metric of space-time, which talks about the distance between points in space-time, also has functions in it, which there wouldn't be in ordinary, like, you know, what we would ordinarily think of space-time.
Mm-hmm.
Okay, so the next level, just like we talked about curvature in like meeting of lines that deviate, related to connection curvature was simply just curvature of a line, like the calculus curvature. And that's going to be related to the metric curvature. Physically speaking, we had the tidal acceleration related to the gravitational acceleration, which is then going to be related to something else physical. So we have these two parallel rows of three levels, right? At the top level, on the math side, we had the Riemann curvature, which measures, right, the curvature of the relative curvatures of things, of geodesics. And the physics side of that was what? What does that correspond to physics-wise? Tidal acceleration. Okay. The next level below it was the connection curvature, right, from which this Riemann curvature is derived. And what physically corresponds to it?
Just the gravitation.
Gravitational acceleration. The next level on the math side, we already said, will be some kind of a metric, a space-time metric. What might be on the physics side? And this has to do with what I said about the structure. Okay? We could write the tidal acceleration or Riemann curvature equation only because it has structure. We write it in terms of the gravitational acceleration.
Mm-hmm.
So there are many, many tidal terms because let's say it's a 3x3 tensor, so it has 9 components, but it can be written, all of those 9 components can be written in terms of the 3 components of the acceleration. So just given 3 things, you can know all 9 things. So the structure that's hidden, that substructure, allows it to be expressed in fewer field equations than you might otherwise think. You don't need 9 field equations for these 9 components of this 3x3 tensor thing. You only need to know 3 numbers because all 9 can be specified by the 3 things of A. It's A prime and A over R and so on. So all you need to know is the 3 components of A and you got it all. But even that is not because we only have one thing on the right-hand side row. So clearly these 3 components of A have a substructure, that there's one thing, that if you give that one thing, you can find all 3. So that's the progression. There's one thing, which we don't know yet what it is, which if you specify that, you can find all 3 components of the vector, A. Given those 3 components of the vector, you can find all 9 components of the tensor tidal acceleration. And in the math side, you have these many Riemann tensor components, which in space-time won't be a 3x3 thing, it'll be a 4x4 thing. It's actually much, much more than R, T, R, T, R. There are 4 different things, and each one is 4 things, so it's 4 times 4 times 4 times 4. Okay. But all of those 256 whatever components can be specified in terms of these gammas, and the gammas have fewer components. There's only 3 indices there: 4 times 4 times 4, 64. What's 64, right? It's a 64 component question. But all those 64 things can be determined by the much fewer metric coefficient things. Okay, can you take a stab, a guess at how many metric coefficient things there are?
16.
Okay, why 16?
4x4.
4 by 4, right, okay. Basically, what do you think the space-time metric is going to look like? Tell me a formula for the space-time metric, like an example. Just like the x squared plus the y squared plus the z squared is a 3-dimensional metric. What will be, but another example of 3-dimensional metric that we saw for spherical systems was what? The r squared plus sine squared or whatever plus r squared, right? A little bit more complicated.
Mm-hmm.
So what will a 4-dimensional space-time metric look like?
Should have 4 components.
Should have at least 4 things, right?
Right. So be space 1. So 3 of those at a time.
Right. Now, a more complicated thing will have functions in front of them, right? You'll have not only the x squared, the y squared, the z squared, maybe something like a dt squared, you'll have functions in front of them. But you can also have a dt times dx and a dy times dt and et cetera, et cetera. Mixtures of all those things. Okay, so a general space-time will have all these different things. Okay? So in other words, you can have a, right, you'll have a dx dt, a dy dt, dz dt, a dx dy, dx dz, et cetera. How many combinations can you make?
16.
Well, for the first thing you can choose 4, and then for the second thing you can choose 4. The diagonal pieces will be the dt, the xx, whatever.
Right.
So these 16 things will specify the 64 things, which specify the whatever it is, 256 or whatever it is.
Oh.
Okay? In real physical situations, though, you're never going to really need 16 things. You can always eliminate because of symmetry and so on. They're going to be far, far fewer than 16. And those will specify these, which will specify those. All right, so now again, we're going to look for how the gravitational acceleration comes from the potential, but we're keeping in mind that it's something very amazing, this gravitational potential. It's not anymore just some silly little thing. So now we can see in a very nice, like, vector calculus way, what it means that A is the gradient of the phi. Now why am I laboring so much over this? And the space-time geometrical significance we know already is going to lead to the metric. Okay, let's look at a diagram of what it means. What does the gradient do? Now we're going to look at this a little bit more, a little deeper. We see that this gradient thing has to do with a special path. It has to do with the shortest distance between contour lines, right? There are things that might be reminiscent, like of geodesics, just kind of vaguely reminiscent. Special paths, shortest distances. You can kind of see an analogy. There's also, when you have a potential, you can define an energy. What does the energy conservation come from? It comes from the fact that no matter which path you go through, there's this quantity which you can call the energy, which is a combination of kinetic energy and potential energy, which remains constant. And again, that's reminiscent. If you think about it, what's a sine qua non, some property that has to be true about a metric? If we're talking about the distance between these 2 points, clearly it doesn't matter like how you go about measuring it, so to speak. The distance between the 2 points is the distance between those 2 points. The quantity doesn't depend, so to speak, on some element of the path. Of course, if you go on a long path and you measure the distance of that path, it'll be longer. But it's a quantity that doesn't depend, it depends on the 2 points. It depends on the endpoints. Like when you do the integral of a path integral, like f dot dr, right, to get the potential. You have an endpoint, 2 endpoints, 1 and 2. This quantity, the energy, will not depend on the path, it depends only on the endpoints. You'll get an integral, and you just plug in this endpoint minus that endpoint, and that gives you the quantity. It's the same thing like a metric has that quantity, has that kind of characteristic. It has something to do with the endpoints. It doesn't have to do with paths between them. So there's all these intuitive kind of connections of relationships that you can make between what we spoke about now, a potential, and the idea of a metric. Okay, to do it precisely and fully, of course, you have to develop this whole theory.
In general relativity, like just like I remember, like say curl is not equal to 0, right? It's equal to some function.
Well, okay, it's something like, just like in Maxwell's equation, you have div b equals 0, but the curl is not. And on the other hand, for E, you have curl is 0, but div, right, is none. You have the electric and the magnetic. Those are two parts of the same thing. Once you've seen Helmholtz, you can see
Yeah,
how they're kind of
in relativity they become the same.
right. They become the same thing. So you can see how they're kind of reflections of each other. They have you almost kind of have to be that way,
Yeah.
right? In Einstein's equation, you can also see it to some degree as like the electric and the magnetic in some sense, but it's more united in that way. Once you're doing it with tensors, you can see it as a whole as tensors, but you can break it down also into something like that. But it's just starting from a much more complex substrate. But again, we can begin to see this three-level structure that we showed before. Tidal acceleration, which corresponds to what in space-time geometry? What does tidal acceleration correspond to in space-time geometry?
Space-time geometry,
Riemann curvature. Okay. Tidal acceleration in gravity can be decomposed into, or is built up from
potential. Well, gravity and then potential.
gravitational acceleration, which in the space-time side is what?
World-line connection curvature.
Exactly. And then in the gravity side, the gravitational acceleration can be built up from the potential, and the connection, we're supposing the space-time connection, just like other connections, spatial connections, can be built up by what we're supposing to be a
space-time, place-of-time curvature.
Space-time metric, which will exhibit curvature. You'll have curvature at these three different levels. The metric curvature, when you look at a metric, you can see it has these functions in it. You think it may be curved. Now, when you look at the dr squared, the x squared, dr squared plus r squared sine squared, you see these functions, it doesn't mean that it's a curved surface. It means what? The coordinate lines are curved.
Right.
So you always have to be careful when you're looking at something. Something is curved, but is it just coordinate curvature which you can get rid of, or is it not? It's just like Riemann curvature tells you that there's real curvature of space-time. If all you know is that there's connection curvature, you can get rid of it, go to free fall frame, right? Space-time connection vanishes. The metric also. The metric, you have to look, check to see whether this metric curvature is just like the r squared sine squared, which is coordinate curvature, or if it's actual space-time curvature. Okay? And again, that's reminiscent. If you think about it, what's a sine qua non, some property that has to be true about a metric? If we're talking about the distance between these 2 points, clearly it doesn't matter like how you go about measuring it, so to speak. The distance between the 2 points is the distance between those 2 points. The quantity doesn't depend, so to speak, on some element of the path. Of course, if you go on a long path and you measure the distance of that path, it'll be longer. But it's a quantity that doesn't depend, it depends on the 2 points. It doesn't depend, it depends on the endpoints. Like when you do the integral of a path integral, like f dot dr, right, to get the potential. You have an endpoint, 2 endpoints, 1 and 2. This quantity, the energy, will not depend on the path, it depends only on the endpoints. You'll get an integral, you just plug in this endpoint minus that endpoint, and that gives you the quantity. It's the same thing like a metric has that quantity, has that kind of characteristic. It has something to do with the endpoints. It doesn't have to do with paths between them. So there's all these intuitive kind of connections of relationships that you can make between what we spoke about now, a potential, and the idea of a metric. Okay, to do it precisely and fully, of course, you have to develop this whole theory.